Hey guys, Clara here. Today we are gonna talk about and solve all the puzzles in the Treasure of Hexagon Island, abbreviated as TTOHI. It means the Treasure of Hexagon Island. Numberblocks episode. It has 4 different math puzzles, and they're all different famous math puzzles, but they're introduced in a way that's more kid-friendly. So they wouldn't get way too complex. They don't want to make the kids way too confused. So yeah, it was a fact. Most of them are even properly solved in the end. Let me just listen to the Helping Hand song. Then to the Put Your Hands Together. Most of them are just done by cheating. Heck, only 4th puzzle is legitimately done. The others are cheating. But now here's how to actually solve the puzzles. First up, ones puzzle. Well, at first it just seems like just needs to get together in the right direction. Like this isn't correct, this isn't correct. Because that have to be in the center. So this is easy peasy, right? But soon it becomes this. It is. Now, when one put this together, he said this: a half and another half makes a whole. Now, on this, she said a half and a quarter and another quarter is a whole. You see what they're referencing? Because I definitely see what they're referencing. We can split this quarter in 2 again, and now we get this: a half and the quarter, and an eighth and another eighth is a whole. We could then proceed to split this eighth into 2 again. We would get a half and a quarter and an eighth and a 16th. And another 16th is a whole. We could practically just split these up forever, right? Like 16 split into 30 seconds, then 64, and then sooner or later we're gonna work with infinitely small pieces like this: a half and fourth and eighth and 16th and a 32nd and 64th and 128, and then you just go on forever. It's an infinite sum, but it adds up to a finite number, 1. Yes, it's that zero problem that bamboozled mathematicians for years. Not years, centuries. It's a zero problem. Is that infinite numbers can add up to a finite sum. Infinite numbers that aren't zero can add up to a finite sum, because obviously infinite zeros are still zeros. Well, for one moment, I actually thought that Hexagon was gonna split that cube into like a half and a quarter, and a bunch of infinitely small pieces. But apparently, Lucy decided that it's way too complex for kids to understand. So Hexagon decided to be a jerk and do this. Now, if they actually split the cube into this, that would be really cool. Even if they never actually solve it, that would still be cool. But they missed that opportunity here. Well, so yeah. Of course, this puzzle was only referenced here. The real puzzle is just put the dots into the center. A really easy peasy one. Just turn all of these, rotation, magical creation. This puzzle was only referenced, but it's still a good reference. So that's all of 1's puzzle. Now let's continue to 2's puzzle, the balancing puzzle. Puzzle number 2, the balancing bridge. Wait, isn't that the name of a previous Numberblocks episode? So the puzzle here is walking plank like this. It is. Now what does it do? It spins around the middle. So what would you do? Now it has to be balanced, which means if there's a one here, there must be a one here. If there's a one here, there should be a one here. If there's a one here, there must be a one over here. So when it start off over here, they progress in symmetrical roots. The roots are symmetrical, obviously, and then they see the roots are definitely symmetrical. Now this works. If you go with symmetrical roots, this will work. But then we can encounter this, which doesn't have any symmetrical roots by this line. So how are we supposed to solve this thing? Now, here's something interesting in physics. It only spins when the center of gravity isn't on this here line. If the center of gravity is on the line, any point in the line, it could be here, here, here. If the center of gravity is on the line, then it's not going to spin. You're not going to get dropped into the water, the poorly made water. Now, so, let's see. If 1, 1 is here, 1 is here, then the center of gravity is obviously let's pretend that the center of gravity on the bridge is definitely on the line. The center of gravity would be here, right? The center of these two. But if now this one just decides to move forward, so 1, 1 is here and 1, 1 is here. The center of gravity, the center of this line would still be on the spinning anything, the center of the bridge. If the one's here, it will still be on the center, see? But if this one moves to here, the center of it's going to be here. It's not getting on the center, they're going to fall into the water. So the ones can move freely, but to move up, they must move inwards or outwards. They must both move inwards or both move outwards. So now that we know that, here's how to actually solve this puzzle. Now the ones start out in this position. Now they both move outwards. Now this one's here, this one's here. Now this one is going to stay in place while this one is going to move forward to here. Now, from what we learned, this is still going to balance the bridge as the center of gravity is still going to be on this line. And now they can both move inwards one block. They both move inwards one space so that they are now here and here. The center of gravity is still on this line. It's still center. And now, look, there's a clear path for this one now. It can now just progress. It can get over here. And now they can both jump off the board. Or if they prefer, they can just get to the middle and add up to 2 again. Now he jumps off the board. Now this is how they actually solve 2's puzzle. Also, on side note, a helping hand on or put your head together or whatever. This does not solve the puzzle. This would not solve the puzzle. If you tried this in real life, you would definitely 100% fall into the water. What are you doing? No, seriously, what are you doing, Seven? I mean, he's just cheating using his dumb luck. Stop cheating, Seven. Now, here's why it wouldn't work. Since the pivot point is here, according to that law of the lever, for the bridge to be balanced, the weight multiplied by the arm must be equal on both sides. Now, when 7 rolls to here, he has 1 block here, 1 box we place here, 1 block place here. Now the total weights found on these sides would both be 7, but the arm would be different. Like this arm, this would be 3, but this would be 2. So, since the weight is the same, but the arm is different, it's just not gonna work out. It's not gonna get balanced. But it gets balanced because of dumb luck. Dumb freaking luck. Also, these ones are just carrying the 8 ball. Come on, you all know how high ones can hop in Numberblocks. They can literally just hop across. But anyway, that should just ruin the puzzle, so nah. Now let's continue on to 3's puzzle. Number 3, the projection. The 3D projection puzzle. Now the contents of the puzzle, what's the puzzle is supposed to be? Create. You know what? I'm just not gonna write IND. This yellow pen is so hard to see. I'm just gonna use brown. Create a shape that projects as a 2 by 2 square in all 3 dimensions. Using less than 8 blocks. Alright, this might seem a little bit too complex to some younger viewers, so let's see, what does projection mean? Well, let's just look at these 3 boards, shall we? Now, when you look from this direction, what do we see? What does this look like? It'll look like this. A 2 by 2 square. See? So it projects as a 2 by 2 square from this direction. But what happens when you look from this direction? It will look like this. It will look like a 1 by 2 rectangle. So the little part of this, yeah. What happens when you look from the top? It will also be a 1 by 2 rectangle. So this is lit up, but this is unlit. So that's basically what projection means. It means like What 2D shape can you see when you look from one of these three directions? Now, let me just use the yellow here as well. Now, it projects as a 2x2 square here, but not here or here. We want to project as a 2x2 square in all three dimensions. Now, what's a shape like that? Most people think of a 2x2x2 square cube first, but that requires 8 blocks, and we want you to make one with less than 8 blocks. You know what? Let's try to make a 2x2x2 cube here. Yes, I add a little bit of wonk. Well, let's say this is a 2x2x2 cube. Now, I am going to take this block off. Okay? I'm going to take away this block, and now it will look something like this, right? And it's now made up of 7 blocks. But if you look from this direction, what will it be? It will be a 2x2x2 square. It would definitely be 2x2x2 square. If we look from this direction, it will also be a 2x2x2 square. Here is a standard F shape, but there's also a cube here, so it fills in down. It fills in. Now, when you look at the top, it's still going to be a 2x2x2 square because this is a step, and plus this one, it's going to be 2x2x2 square in all of these directions. In fact, you don't even need 7 blocks. You can do it with 6 blocks. We can also remove this block here. Now you can't see that clearly, so I'm not going to remove the out block. Instead, I'm going to move these 2 blocks. Remove this. It's going to look like something like this. And now let's remove this. Look a bit like this. And yeah, here it is. This only has 6 blocks, but it's also still gonna be a 2x2 square in each direction. Don't believe me? Try yourself. 1, 2, 3, 4. I'm just gonna explain this. 1, 2, 3, 4. We look from top. 1, 2, 3, 4. So we can literally do it with only 3 blocks. I mean 6 blocks. We can't do it with just 3 blocks for us. In fact, we can literally do it with only 4 blocks if gravity doesn't exist. We can remove this off the bottom. Like, I'm gonna make this cube float now. This cube is now flowing. This cube is now flow. And now I'm gonna remove whatever that's on the cube that's on the bottom of this cube. You can't see it, but it exists, and now it's gone. So now there are 1, 2, 3, 4 cubes. That's when you look from the front, it's 1, 2, 3, 4. When you look from this side, it's still 1, 2, 3, 4. When you look from top, 1, 2, 3, 4. It's always gonna be a 2x2 square. Well, we have However, we have two floating cubes here, and that's not going to work here. Gravity exists, so we need at least 6 blocks for this. But still, you don't need 8 blocks. You only need 6. 6 is the minimum number needed for this. Of course, like there's an existing block here. Three more stones in this. 3 more cube stones in the swamp, and plus the number block 3, that equals 7 blocks. It provides 7 blocks, not 8. But that would be enough. That's actually more than enough. Also, keep in mind that Captain Hexbeard actually has no idea what this is about. Since, this is an actual puzzle, but Hexbeard said to make a cube, show her a cube has two blocks, 2 blocks wide, 2 blocks deep, and not something that looks 2 blocks wide, 2 blocks tall, and 2 blocks deep from each direction. Okay. I'm pretty sure Hexbeard also has no idea what this is talking about. This is the actual puzzle, though. This is the real puzzle. What Hexbeard said? That's impossible if 5 just didn't just dump out that portal or something. And now, that's puzzle number 3 then. Now let's move on to puzzle number 4. Everything's a puzzle, a mystery to me. This too forward, or puzzle 4. Square counting. Like, this one is a pretty easy one. Like, it's just count squares. So, how many squares are in this? 1, 2, 3, 4. That is at first glance, right? But then you realize that this whole thing is also a big square. So after you count the big square in, that'll be 5. 1, 2, 3, 4, 5. When you write that as an equation, you get 4 little squares plus 1 big square. And now we have this 3 by 3 square, which is more complicated. But first, we can look at the 1 by 1 squares. 1 by 1 squares. How many 1 by 1 squares are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 1 by 1 squares, right? Now we can look at 2 by 2 squares. How many 2 by 2 squares are there? 1, 2, 3. There's one on every corner. 4. There are 4 2 by 2 squares. Now, how many 3 by 3 squares are there? 1. It's literally a 3 by 3 square. There's only 1. So 9 plus 4 plus 1 equals 14. Wait a second. 9, 4, 1? Aren't those also all square numbers? I think we see a pattern here. Well, now it's time to prove that pattern. Let's say we have this. We have a square from puzzle square. You know how tall is that exactly? How many blocks tall? How many blocks wide? Oh, it's 6 blocks tall by 6 blocks wide. Hold on. Let me just draw the grid. 6 plus 6, 6, 6, 6, 6. Now it's a 6 by 6 square. Alright, now see. How many 1 by 1 squares are there? Now we can also use that projection thing from this one. Well, it could be on the first row, it could be on the second row, it could be on the third row, it could be column. It could be on the third column, it could be on the fourth column, it could be on the fifth column, it could be on the sixth column. There, the sixth column is you can choose from. It could be on the first row, it could be on the second row, it could be third row, it could be fourth row, fifth row, sixth row. It could be in six columns and it can be 6 rows. So the total number of places it can be is 6 times 6 is 36. See something here? Now let's see 2 by 2 squares. Now we're talking about columns. That's over 2 columns. So it can be on columns 1 and 2, and it can be on columns 2 and 3. It can be columns 3 and 4, 4 and 5, 5 and 6. So it can be on 5 horizontal locations, and since it's symmetrical, it's the same thing for vertical locations. It has 5 types of horizontal locations and 5 vertical locations. So the total number of locations it can be 5 times 5 with 5. So that's the total number of 2 by 2 squares on different locations. Now let's see. Now, what about 3 by 3 squares? Well, it spans 3 blocks, so it can be on 1, 2, 3, or 2, 3, 4, or 3, 4, 5, or 5, 4, 5, 6. How many types is that? That's 4 types, right? So there's 4 horizontal locations it can be on, and 4 vertical locations it can be on. 4 times 4. Now, what about the 4 by 4 squares? The 4 by 4 squares it spans 4 blocks, so 1, 2, 3, 4, 2, 3, 4, 5, and 3, 4, 5, 6. It has 3 types of horizontal locations and 3 types of vertical locations. Now we have the 5 by 5 square. Now on this side, it can be on 1, 2, 3, 4, 5. It can span over 1 to 5, or it can span over 2 to 6. There are 2 types of locations it can be at. It can be located at 1 to 5, or it can be located at 2 to 6. That's for horizontals. For verticals, that's another two types of locations. So there are a total of 2 times 2 equals 4 locations that 5 by 5 square could be at. Now, a 6 by 6 square, this whole thing is literally 6 by 6 square. So, plus 1. Now, what does that equal? See, it's just the first 6 squares add together. Let's see, 36, 25, 16, 9, 4, and 1. Now we know this 14 is 30, 55. 55 plus 85 is equal to 91, the number that's both lucky and unlucky. Or as I like to call it, the Nakito number. Now this 91 here is a square pyramid. And that next time someone asks you how many squares are in this square, you know once it's gonna be a square pyramid. It's gonna be a sum of squares. And so that's fourth puzzle finished. Well, five puzzle is mostly about helping, and so same with sixth puzzle. They're all about friendship. It doesn't have much to do with math. So yeah, I guess that's basically the end of this video. Bye!